Okay, good afternoon, everyone. Welcome to our third edition of this NITheCS Mini-school modeling optical spectra. And this is being hosted by Professor Tjaart Krüger, University of Pretoria, and Dr. Towan, Nöthling. So welcome to everybody here present today. Also, I would like to remind everybody that this is being recorded and will be on YouTube most probably by tomorrow. So please remember, if you'd like to share this or if you can't make the whole session, please remember the value of the YouTube recordings. Towan, thank you very much. Thank you very much, Dr. Tjaart, also for putting this together. Thank you. Have an awesome afternoon. And also, can I ask you, Tjaart, if you can handle the questions at the end? Thank you. Okay, all the best. Towan, over to you.
Thank you very much. I suppose you can all hear me.
Perfect, perfect. Yes. And we can see your screen also. Perfect. Thank you.
Cool. Okay, so I hope to give you an overview of linear and nonlinear optical spectroscopy. So my research work in the biophysics group of the University of Pretoria focuses on using spectroscopy and spectral modeling to study photosynthetic systems. So like the photosynthetic systems you see in the trees in the forest. Now, physics talks contain a lot of equations, and it is difficult to discern the forest from the trees, as it were. So we are going to take one route through the forest of spectroscopy. There are, of course, many routes, and there will be aspects of spectroscopy that we don't get to. I'm also going to show a lot of equations. The most important ones I'm going to highlight in red boxes. But you should remember that an equation is a picture of reality. So equations tell us stories about reality. You shouldn't memorize these equations, nor should you even understand them in detail. But I hope that by the end of the school, you'll be able to, in plain English, tell yourself the story of part of spectroscopy. So let me first give you an aerial view of the forest, an aerial view of spectroscopy. So in a spectroscopic experiment, we of course illuminate the sample. We will only consider solids. We illuminate the sample with light, and we also detect light. So what happens in a spectroscopy experiment is that the light causes a polarization, actually a fluctuating polarization within the sample. And this fluctuating polarization in turn causes an electric field, which I show here in green. And we sometimes observe this induced field. Other times, like in an absorption spectroscopy experiment, what we observe is actually the interference between the incident field, the field that we use to eliminate the sample, and the induced field. So what we will see is the gray dotted line, the interference between the two, the induced and the incident beam. Okay, so to give you a 1-minute summary of what we are going to discuss, first we're going to look at Maxwell's equations and how they relate the induced polarization in the sample to the measured electric field. We are going to look at the different orders of polarization and relate them to different orders of spectroscopy. So linear spectroscopy relates to the first order polarization, and nonlinear spectroscopy relates to the nonlinear orders of polarization. We're also going to look at spectral signals and how they can be calculated from the system response functions. Now, this can be done using classical physics, but in order to go further, we need quantum mechanics. Using quantum mechanics, we are going to discuss how the polarization depends on the quantum dynamics in the system. We will calculate the linear response function, which relates to the linear spectroscopy, like absorption. We are going to discuss an exact method for calculating linear spectra, and we will be calculating approximate spectra. Okay, so we start with Maxwell's equations. The next 6 or so slides will be basically a summary of what Prof Thomas Manchal of Charles University presents in a series of YouTube lectures on nonlinear optical spectroscopy. I strongly encourage you, if you're interested in the field of spectroscopy, to watch these videos. He explains the field very well, but the videos are also very, very dense. So maybe this lecture is a good introduction. We start with Maxwell's equations, which are the classical electrodynamics equations. And then we do a fairly standard derivation. We work in terms of the electrodynamic potentials, and we work in the Coulomb gauge. Then we rely on the Helmholtz theorem, which says that the electric field, or any vector field for that matter, can be separated into tangential and orthogonal components. And it is these orthogonal components that form part of the propagating electric field, or part of light for that matter. So making use of this derivation, we also relate the current density to the polarization density. Making use of these derivation methods, we derive this equation. This is an inhomogeneous wave equation for the electric field, which means that it has a source term. The source is the polarization within the sample. And this equation tells you how the electric field that propagates relate to the polarization within the sample. Okay, so if we take this sample and we Fourier transform it, this is a standard approach in solving differential equations, we get this equation. Now, something else that we will do, which is an important assumption. It's basically not an assumption. It is we expand the polarization in terms of different orders of the electric field. We do a Taylor expansion of the polarization. Most materials are not permanently polarized, so we can disregard the first term. And for the moment, we'll also discard the nonlinear terms, those terms that depend on nonlinear orders of the electric field, although they will be important for nonlinear spectroscopy later. So for the moment, let's only consider the first order term. So the first order term has the first order susceptibility in it. Plugging this first order term into this equation leads us to this expression. I hope you can all see the laser pointer. This expression, and since the electric field is not always zero, this first part of the expression must be zero, from which we can then calculate the wave number as this expression based on the linear susceptibility. For clarity, I haven't included this one in parentheses there, but this is the linear susceptibility. The linear susceptibility has a real and an imaginary part. And after some fairly easy algebra, we can write the wave number in this format, consisting of a real part and an imaginary part. Now, if we were to consider the electric field, which we assume propagates in the z direction, at one instant of time, so we take a snapshot of the electric field, we know that the electric field is proportional to e to the I kz at one instant of time. So the intensity is the square of the electric field. But if the electric field is given by e to the I kz, then we can inspect what the different terms of k does to the field. The first term is the refractive index that changes the density or the speed of light within the sample, whereas the second term, which has an imaginary number in it, multiplies with this imaginary number to give you attenuation. So we have attenuation of the electric field, and therefore also attenuation of the intensity. The attenuation of the intensity is frequency dependent, and we can characterize it by the absorption coefficient, which is what we measure when we do an absorption experiment. Now we see that the absorption coefficient is proportional to the imaginary part of the susceptibility. In other words, we can get spectroscopic information, the absorption coefficient, from the susceptibility, more specifically from the imaginary part of the susceptibility. This result specifically holds for first order polarization, but as we will see later, it also holds in general. We can get spectroscopic information from the susceptibility. Okay, so we spoke about these susceptibilities in the expansion of the polarization. We spoke about the linear susceptibility, which gives rise to linear spectra. And we spoke about nonlinear susceptibilities, which give rise to nonlinear spectroscopy. The susceptibilities are frequency dependent. That is, they are functions of frequencies. In this expression, also the polarization and the electric field are functions of frequency. We can write a similar expansion for the polarization in terms of time, in the time domain. So again, we have the 0th order contribution, which we'll ignore, then a first order and second order and so on. Now, we can calculate the nth order of polarization using this monstrous equation. It looks quite convoluted, but it's really not that bad. All it says is that the nth order polarization at a point in time, t, so let's say we observe the polarization at time t, the nth order polarization has to do with n interactions with electric fields. So if we were to consider pulsed electric fields and we assume one interaction per pulse, then we can say that the nth order polarization has to do with interaction with these n pulses. So first with the green pulse, then with the blue pulse, and then with the red pulse. But the nth order polarization also depends on, of course, on how the system responds to those electric fields. So the nth order polarization depends on the nth order response function. You'll hear that name again later, it's response function. And we can relate the first order susceptibility to the first order response function via Fourier transformation. This means that, in effect, we can calculate the absorption spectrum, which is the first order spectroscopy method. We can calculate absorption from the first order response function. Okay, so a brief summary. We have seen that the propagating electric field relates to the polarization within the material. Then we expanded the polarization in orders of the electric field, different orders of polarization, and we considered the linear part of this expansion. We showed that the absorption coefficient is proportional to the imaginary part of the linear susceptibility, that is, that spectroscopic results relate to the susceptibilities. We showed that the nth order polarization can be calculated with this equation. The nth order polarization relates n interactions with electric fields to the nth order response function, and we can calculate susceptibilities from response functions. In this case, the linear susceptibility from the linear response function via Fourier transformation. Okay, so to get more detail, we have to consider the quantum mechanics of the system. For this, I'm going to consider a photosynthetic system, with a system in green sulfur bacteria. So in these bacteria, the photosynthetic apparatus consists of a chlorosome, which has many pigments. This chlorosome absorbs light, and the light is transferred through the bacterial chlorophyll A base plate to something called the Fenner-Matthews-Olsen trimeric complex, which we will consider now in more detail. From the FMO, Fenner-Matthews-Olsen complex, excitation is transferred to the reaction center from where energy-rich compounds are manufactured. So now let's consider the FMO trimer in more detail. Here I show that the FMO trimer. This trimer consists of many pigment molecules. In each monomer, there are many pigment molecules, the dark blue interiors. And these pigment molecules are embedded in a protein framework. The protein is shown in yellow and purple ribbons. So I show the pigment molecules, the chlorophyll molecules of this monomer there on the right-hand side. Now, the protein structure is flexible and it fluctuates because of thermal fluctuations. And these fluctuations induce changes in the energetic landscape of the pigment molecules. So we need to take environmental or protein fluctuations into account when we model spectroscopy. That will be important later. Okay, so let's consider a single chlorophyll molecule. Chlorophylls are typically electrically neutral, or they are always electrically neutral, but we can induce a transient dipole moment, as Prof Krüger discussed in the previous lectures, with light. So when we shine a light on chlorophyll, an electron can be promoted from the ground state to the excited state, and we say that the chlorophyll becomes excited. The dipole moment, the transient dipole moment, is indicated by the red arrow and denoted by mu. Okay, so the radiation matter interaction is a semi-classical Hamiltonian. It is simply the coupling of the quantum mechanical transition dipole moment operator with the classical electric field. The transition dipole moment operator is given by this expression, and you can see that it effectuates transitions between the ground and the excited state. By the way, this ket with N in it denotes a state in which pigment N is excited, whereas the G denotes the ground state. Okay, so we also need to discuss the electronic Hamiltonian. So let's consider a system of two chlorophyll molecules with the dipole moments as indicated. Each of them has a characteristic transition frequency, the energy required to go from the ground to the excited state. And these energies feature in the Hamiltonian. There they are, the epsilons. But because of the transition dipole moment, the pigments can also couple to one another. That is, they can interact to form exciton states. In the shown configuration, the dipole moments point towards one another. So this is a J aggregate, meaning that only the lowest exciton state has appreciable dipole moment. We'll see only transitions between the ground state and this lowest exciton state. We also need to describe the nuclear positions because as I said earlier, in the Fermi-Matthews-Olsen complex, the protein changes, or it is essential to take fluctuations within the protein, that is nuclear fluctuations, into account when we model spectroscopy. So we will model the nuclei as an infinite set of harmonic oscillators. In the electronic ground state, the nuclei will therefore oscillate as harmonic oscillators, and in the electronic excited states too, but the equilibrium position in the electronic excited state is somewhat shifted. That means that we have oscillating nuclei, and as soon as we effectuate the transition to the electronic excited state, the position of the nuclei change, but they still fluctuate as oscillators. The difference between these potential energy surfaces are linear, as you can see here. That points to linear interaction between the electronic and the nuclear modes as we will see much later. We refer to the nuclear set of nuclear oscillators as the bath. Okay, so the molecular Hamiltonian consists of the electronic Hamiltonian and the nuclear Hamiltonian. Now, in order to go further, we first need to introduce some concepts from quantum mechanics, which some of you may be familiar with. Let's consider a system S with 2 chlorophyll molecules, and we make this superposition state. This is an exciton state. So in the first part of the superposition, only pigment molecule 1 is excited. In the second part, only pigment molecule 2 is excited, but we create this superposition. Now we can write something called the density matrix as this expression. Sorry, this is the density operator, but an operator has a corresponding matrix, so we can consider the density matrix. On the diagonal entries are the Born rule probabilities of finding the system in that particular state upon measurement. So alpha square of finding the system in the state in which only pigment molecule 1 is excited. And on the off diagonal of this density matrix are the so-called coherences, which give us an indication of the collaboration of the 2 states to form a superposition. There's something called a trace operation, which we can perform on both matrices and operators. And for a matrix, that simply means that we add the diagonal elements together. So we said that the diagonal elements are the probabilities. So it should make more or less sense that the expectation value of an operator is given by the trace of the operator times the density matrix. Now, systems are never isolated. In the Fermi-Matthews-Olsen complex, we also don't have the pigment molecules in isolation, but they are embedded in a hot and messy protein environment. So we also need to take into account the environment. And these environmental states are typically entangled with the system states. We can calculate the density matrix for this full system, as we did before. And we can calculate something called a partial trace, in which we average only over the environmental degrees of freedom. So we can hand-wavingly say that we can calculate the average over the environmental degrees of freedom of an operator A by calculating the partial trace of A times rho. If we leave the system, that is the pigment molecules, in their environment for long enough, eventually the system will reach equilibrium. We denote that equilibrium state by the equilibrium density matrix. Okay, then the last thing, in order to evolve the density matrix in time, we have to evolve from both sides. So we have to evolve the ket as well as the bra. So this is the way in which we evolve a density matrix. We can denote this in shorthand notation using this script U. And this script U is called a super operator, which sounds really fancy. But we also introduce this V super operator, which basically means it's a super operator for the dipole moment. So you don't need to worry about this. You can just think of the script U as something that evolves the system, and as the script V as a transition, a dipole moment operator, dipole moment super operator. Now, back to the quantum mechanics of the response. We say that the nth order polarization depends on n electric field interactions and also on the response function. Now we want to inspect this response function and see what form it has. It's not too difficult to understand. The nth order response function has this form. We start with the system in equilibrium. So before anything happens, we assume that the system has equilibrated with its environment. It's happily sitting there in equilibrium. Then, when the first electric field interaction arrives, let's look at pulsed electric fields. So when the first pulse arrives, this we strike the system with a dipole moment interaction, and then it evolves again under the molecular Hamiltonian until the next pulse arrives. When we strike it again with the dipole moment operator, and it evolves under the molecular Hamiltonian. When another pulse arrives, we strike it again with the dipole moment operator, and so on. And then eventually we calculate the expectation value. One thing to notice, which is important, is that between the interactions, whether the electric fields were pulsed or not, between the interactions, we evolve the system using only the molecular evolution operator. That is, between the interactions, we don't take into account the light-matter interaction, which makes calculation of the response function much easier. The only times when we worry at all about light-matter interactions are these brief strikes with the operator. Okay, so from this expression for the nth order response function, we can calculate easily the first order response function, which has this form. Now there's only one dipole moment superoperator. Okay, we just saw that we can calculate the first order response function in this form. And by doing some algebra, we can rewrite this expression in this form. This theta is the Heaviside step function. It just prevents anything from happening before the first interaction. And these r's I will also refer to as the linear response function from now on. Notice that there is a difference between the script r and this non-script r, but this non-script r basically contains all the information in the script r. They are basically the same thing. So let's speak about this thing as the linear response function from now on. So in the script r, we had a commutator in this script v. We expanded that commutator in this expression, so now there's no commutator in this r. But this response function has this form. Here we evolve the dipole moment operator in time. So basically what we see is that the first order response function has this form, a form of a correlation of the dipole moment operators. This is not too difficult to understand. It means that the response function, remember, is how the system responds to interactions with the fields. It means that the first order response function is simply a measure of the fluctuation of the dipole moment. So we ask the question, how does the system respond to interaction with light? The answer is that we can see the response by simply following how the transition dipole moment changes in time. Now, to calculate absorption spectra, we will assume that the system is in equilibrium initially, as always, but we will also assume that this equilibrium state is separable. That means that we have the electronic system in the ground state and the bath in the bath equilibrium state. We can write this expression in this form. Don't worry, notice that there's no red blocks around these equations, so not too much to see here, but for completeness, we write it in this form. And then we can write the response function in this form, and finally in this form. What is important to note here is that the response function basically has two contributions. One from the transition dipole moments, and one from something which we will later call the spectral tensor. Now, finally, we can write the absorption spectrum as the Laplace transform of the linear response function. So as promised, we can now write the spectroscopic experimental results. We can write the absorption spectrum in terms of the response function. Like I said, the response function has these two contributions, and so too does the absorption spectrum. The first contribution is the dipole factor matrix, and the second contribution comes from the spectral tensor. We will discuss these terms independently, the dipole factor matrix and the spectral tensor. We can also calculate with a similar expression the emission tensor, the fluorescence tensor. I will not spend much time on this expression since we have already so much to discuss. Now, just again a summary, we can calculate the nth order polarization based on n interactions with electric fields and on the response of the function of the system. The nth order response function can be calculated using this expression, which basically is iterative application of a dipole perturbation by light followed by evolution of the system, and then again a dipole perturbation by the light, evolution of the system. The linear response function can be calculated with this expression, which we can rewrite as this expression. We will call this thing also the linear response. The absorption spectrum can be calculated as the Laplace transform of the linear response function, which can be written in this way for absorption and emission spectra. So the absorption and emission spectra contains two contributions. Firstly, the dipole factor matrices in purple and the spectral tensors in blue. Let's first consider the dipole factor matrix. The dipole factor matrix depends on the configuration of the system, on the dipole moments, specifically on the dipole moments within the system. I again consider the Fermi-Matthews-Olsen pigments here. But the dipole factor matrix also depends on the type of spectroscopy that we perform. So for absorption spectroscopy, the dipole factor is given by this expression. We can also perform circular dichroism spectroscopy. In circular dichroism spectroscopy, we first insert a left circularly polarized filter in the light path and calculate the absorption spectrum, or measure the absorption spectrum. Then we insert a right polarized filter into the light path and measure the absorption spectrum. And by calculating the difference of those two measured spectra, we can calculate the circular dichroism spectrum. The circular dichroism spectrum can be calculated with this dipole factor matrix. The red part is the displacement between the position vector between two pigment molecules, and the purple part is a cross product of the dipole moments of two pigments that are being considered. Lastly, we can calculate the linear dichroism spectra. Linear dichroism spectra, or a linear dichroism spectrum, is the difference spectrum obtained when orthogonal linear polarizers are used in the light path. We do this experiment, spectroscopy experiment, very roughly speaking, by aligning the complexes like plates in a dishwasher. And then for the linear dichroism dipole factor matrix, we have this expression, and this angle refers to the angle between the particular pigment's dipole moment and the normal vector of the plate in the dishwasher. So the normal vector of these stacked complexes. Okay. Now we have seen how we can calculate the dipole factor matrix. Now we turn our attention to the spectral tensor, which is a bit more difficult to calculate. And the rest of the lecture will be mainly about calculating the spectral tensor. Because once we can calculate this, and we already know how to calculate this, then we can calculate the absorption spectrum. So the spectral tensor. We considered the radiation matter Hamiltonian, the electronic Hamiltonian, the nuclear Hamiltonian, and we said that the molecular Hamiltonian is the sum of the electronic and nuclear Hamiltonians. Now let's partition this molecular Hamiltonian in another way. We will consider the molecular Hamiltonian as having a system part and a bath part, and then a system bath interaction part. The reason for this is that we can consider this system bath interaction part fairly small and then perform perturbation expansions. In this partition, the system part is just the electronic Hamiltonian. The bath part is an infinite set of harmonic oscillators. Notice now there's no shift upon electronic excitation. It's just an infinite set of normal harmonic oscillators. And the system bath interaction part is linear in both the system operators and the bath operators. So this is where that linear coupling between the electronic and the nuclear degrees of freedom comes in. The system bath interaction is how the pigments are perturbed by fluctuations in the protein. For a good overview of open quantum systems, also addressing what we explain here is you can see this book. Just notice that the co-author is Prof Tjaart Krüger. Okay, so we have this partition of the molecular Hamiltonian, and we are after the spectral tensor. The spectral tensor we can write after some algebra in this way. The first part of the spectral tensor of this expression has to do with unitary evolution of the exciton states. So it treats formation of the exciton and unitary evolution of these exciton states. The interesting bit is the system bath interaction Hamiltonian. So let's go back to the Fenner-Matthews-Olsen complex. The protein structure fluctuates, and these fluctuations cause fluctuations in the transition energies of the pigment molecules, as you can see here. So we can plot these deviations as a function of time, and we see that it is a random walk. But when we do many trials, we see that these random walks form a Gaussian distribution or a normal distribution. Now, the average of the energy deviation is 0. And we see that the fluctuations are correlated in time with a correlation function which depends on the environment. It depends on the, let's say, the protein structure. But this correlation function in time still has to be such that this deviation, that the statistics conform to normal statistics, to Gaussian statistics. Lastly, we also say that fluctuations on different pigment molecules are not correlated. They fluctuate independently. Now we consider an exact method to calculate linear spectra. This method was expounded in this article by Moi et al. And deriving this exact approach is, as you can imagine, quite complicated, but I will ask you to squint really hard, and then you can see that the spectral tensor has more or less this form. It's more or less a trace over the bath of some exponential function which has a factor of time. See, there's the factor of time, and when you integrate it, there's a factor of time as well. And lastly, this equilibrium bath equation. So more or less, very more or less, the spectral tensor is the average over the bath degrees of freedom of some exponential function. Now, we know that an exponential function can be generated using this differential equation. So our plan will be to solve such a differential equation a large number of times stochastically, and then take the average of the result. And that is exactly what we do. We have this differential equation, and inside this differential equation, it's a stochastic differential equation. Inside this differential equation, we have the random walks. We then average over many such random walks, and we obtain, after averaging, the spectral tensor. This approach is slow because we have to average over sometimes more than 1 million random walks. So this, although this approach, this numerical approach is exact, it is slow, and for practical applications, we have to use approximate methods. Now, again, if you squint very hard, you can see that the spectral tensor is given more or less in this form as an exponential function. But we have seen that these fluctuations, the energy level fluctuations, conform to Gaussian statistics, and a Gaussian distribution is fully characterized by its mean and its variance. So the plan is to expand the spectral tensor in the cumulants of the system bath interaction. Cumulants just mean the mean and the variance and so on. But we know already that the mean is 0. So what we expect to find if we execute this plan is the spectral tensor in more or less this form. The first part deals with the unitary evolution, that's boring. The second part deals with the system bath interaction, and since the system bath interaction is characterized by Gaussian statistics, we will expect to find only up to the second order cumulant, or the variance in this expression, excuse me. And that is exactly what we find in a method called the full second order cumulant expansion method. We find this expression that I just showed. This deals with unitary evolution, and this deals with the energy level fluctuations due to the interaction of the environment. As you can see, I'll not go into detail here, but as you can see, this K matrix has only the correlation functions. That is the correlation functions of the bath in it. As we expected, we didn't expect, or it's a second order cumulant expansion, so we only will see second order correlations, which is correlation between 2 time points. Okay, this expressions are not exact because it's an approximate method, although for a single pigment in an environment, these expressions are actually exact because, as I said, the Gaussian statistics can be fully described based on the mean and the correlation function. So for a single pigment molecule, these expressions are exact, but when we have exciton formation, then these expressions are no longer exact. We can then perform something that we call the secular approximation. That is, we disregard transfer between the populations in the density matrix and the coherences. I expect you won't understand what I say now. That is fine. You can go back on the YouTube video. And after making the secular approximation, we get the complex time-dependent Redfield method. I'll also not discuss these equations, although this is a fairly accurate method and also not too computationally complex. So if ever you are in need of a method to calculate linear spectra, I would recommend looking at this one, complex time-dependent Redfield. We can also calculate approximate spectra using the modified Redfield method, which is fast but inaccurate. Or we can calculate using the Redfield method, which is even faster and also not very accurate. So in the next lecture, I will briefly consider this part in more detail, this method in more detail. We did a comparison of the accuracy of the different approximate methods in this article. I will not show you the results. It will take a bit long to explain in the time that we have now. But you're welcome to go look at that article. And then I want to give you some resources to delve deeper into this topic. So the first is a series of texts on LibreTexts by Andrei Tokmakov. This is a great lecture series on nonlinear spectroscopy. And then there's also this lecture series that I alluded to earlier by Prof Tomasz Manchal from Charles University about nonlinear optical spectroscopy, but he also goes into detail about linear spectroscopy. Then there are these two books. This is a book by Falkunas, Abramavicius, and Manchal. Gives a good overview of both linear and nonlinear spectroscopy. And then there is this book by Shaul Mukamel, Nonlinear Optical Spectroscopy. This book is very well written, but I must also warn that it is quite dense, so I wouldn't consider this book for beginners. Then not dealing with spectroscopy directly, but with the relating theory, photosynthetic excitons by Van Amerongen, Volkunas, and Van Grondele, the theory of open quantum systems by Breuer and Petruccione, and charge and energy transfer dynamics in molecular systems by May and Kuhn. Yes, so that was me. Any questions? I'm a bit faster than I anticipated, so we have lots of time for questions.
I think I just want to say, while we're waiting for people to formulate their questions, just thank you very much to everybody for attending in person or online today. And remember that for those that joined us slightly later, this recording will be on YouTube, most probably from tomorrow. Would anybody like to type something in the chat, or we can just put up your hand if you have a question, then we can allow you to talk. Special welcome also, I see Ludmila is here. Ludmila Moshkaleva, somebody that gave a talk here in Stellenbosch recently. So it doesn't, okay, there we go. There a question popped up. Let's see, Tjaart. I hand over to you to handle that.
Okay, yeah, thank you, Renee. Thank you very much, Towan, for an excellent talk. So we have one question here from Muhammad Wakas Hasib. Is there only thermal fluctuations?
So I can't see the question, but fortunately it's a short one.
Yes.
Well,
So there's an additional question. The question relates to FMO complexes. So are there only thermal fluctuations in FMO complexes?
okay. So there are thermal fluctuations. I suppose the fluctuations that the physical fluctuations are only due to thermal fluctuations. In gas phase spectroscopy, one has rotation and also Doppler broadening that one has to account for. But when modeling solid state spectroscopy, we only typically take into account thermal fluctuations. That gives rise to homogeneous broadening. But there are also population time broadening, which means that there's a relaxation of the excitation between the exciton states, and due to that relaxation, no single exciton state is permanently populated, which gives rise to lifetime broadening. So because there's uncertainty in the time that an excitation will spend in a certain exciton level by Heisenberg's uncertainty relation, there's also uncertainty in the energy, which gives rise to another source of broadening. Then there's also inhomogeneous broadening in the line shape. Inhomogeneous broadening is due to no two FMO complexes being identical. So there will be small changes in conformation, let's say, and that gives rise to inhomogeneous broadening. So thermal fluctuations is one source of line shape broadening. There are also others, mainly lifetime broadening in solid state spectroscopy and inhomogeneous broadening. I hope that answers the question.
Thank you, Towan. If I could add that, I would like to refer to my first lecture, the first lecture in the series, where in the end, I very briefly discussed different sources of line broadening. So the dominant ones have been mentioned by Towan, but there are also some other sources of homogeneous and inhomogeneous broadening. And those sources of broadening operate on relatively short time scale. Then for these are protein complexes, pigment protein complexes, and they also have another type of disorder that features on longer timescales, and we call these a static disorder, or static here refers normally to the timescale of the experiment that is performed. So, and these types of fluctuations would then arise from different conformations of the protein. Actually, if we talk about different protein conformations, that also features on many different timescales. So you have the ultra-fast timescales to the second or even tenths of seconds timescale. But if one talks about conformational fluctuations in proteins, that's normally fluctuations between active and inactive states, or between different functional states, and that happens on timescales ranging from microseconds typically to many seconds. Mohammed, yes, please go ahead. While we are discussing your question, you're welcome to ask a follow-up question or make a comment on that.
Hello.
Hey, Mohammed.
Yes, I can hear you. Go ahead.
Yeah. My question is that if we want to mimic the nature, so we need the kind of like a solid state material for that. So is there so the only thermal fluctuation is necessary in modeling that to mimic the nature, like in photosynthetic complexes. But when we going to the artificial system, we need to take care of like the solid state materials. So is there so also the only thermal fluctuation is enough for modeling or mimicking the nature?
That's a good question. I have very little experience with artificial systems. But I imagine as long as you can model the environment as a heat bath, then you can use a similar approach to what we have done. So I suppose one would have to model excitons differently in semiconductors. Let's say if you were to consider an artificial semiconductor material and model its spectroscopy, and therefore one I suppose the coupling between the excitons and nuclear modes would also be different. So I suppose one may have to treat the thermal fluctuations differently, but they will always be present and an important part of the spectroscopic response. Yeah, that's unfortunately as far as I can answer you.
Okay, no problem. Thank you.
Thank you.
Thank you.
Thanks for the excellent question. Let's move on to the next question. That's by Joshua Botha. He said, "Hi, Towan. Thank you so much for the talk. Really great. My question is about the exact method. I find it surprising that the exact method uses statistical methods. Could you comment on that counterintuitive approach?"
Yes, that is a good observation. So maybe I can go back to this slide. In the exact method, we have this expression eventually that we use to model spectra. And this expression is numerical. The reason it's numerical is that there is no closed form exact analytical method that you can use to calculate the spectrum. So there is no analytical method that you can use. You have to use a numerical method. And in this particular, there are other ways of calculating exact spectra as well. But in this method, the way we calculate the numerical spectrum is by use of stochastic differential equations. And in order to perform stochastic integration, one has to consider random walks. And the random walks have to conform to certain statistics. So what we do basically is we use random walks to calculate the numerical, the exact spectra numerically, and the random walks have to conform to certain statistics. I hope that answers the question.
Okay, great. So I see another question in the chat. So by Mamaru Alem, great talk. Some of the concepts are beyond the molecular orbital theory we know in chemistry textbooks. I am wondering how this will be represented energetically.
Sure. Another good question, which I don't know the answer to. So I showed you the ground and the excited state of the exciton levels. Basically, one can consider the ground state as the HOMO level, as the HOMO molecular orbital, and the excited state as the LUMO, with electrons being promoted from the HOMO, which stands for highest occupied molecular orbital, to the LUMO, which stands for lowest unoccupied molecular orbital. So we do use molecular orbital theory. In that sense, we basically don't really care about the particulars of the orbitals theory that we use. We don't perform DFT. It's not necessary as long as now I have to go back quite some year. As long as we can calculate the electronic Hamiltonian. And to calculate the electronic Hamiltonian, we only need the transition energies of the pigment molecules and the dipole-dipole coupling between them. So it's almost never necessary for us to know the details of how the of which orbitals the electrons inhabit, as long as we can calculate, as long as we know the energies and the coupling between them. Mamoru, I don't think that answers your question completely, but that's the answer that I can give. I hope that is satisfactory.
Okay, excellent. Thank you.
Michael, I see there's another question from Michael. Yeah, if I can read it, is there
Yes,
any
please read that
software?
out.
Is there any software that one can use to calculate and plot the spectra? That is a very good question. I know that on the webpage of a researcher called Mike Rippert, there was he had software to calculate the spectrum. There's also a software suite called QuantaRay. I'll type it in the chat. And with QuantaRay, one can calculate linear spectra very well, and also some nonlinear spectra. But in the next lecture, I will also give you a very brief way to, we will very briefly consider the calculation of spectra. I'll just type the name of the researcher on whose website you can look. He had a program years ago. I don't know if he still has it. And then there's a software suite called QuantaRay.
Thank you, Towan. The software developed by Mike Rippert is called Pigment Hunter.
Sorry, can you repeat that? I didn't quite catch that.
Sorry, I see my connection. The software from developed by Mike Rippert is called Pigment Hunter.
Thank you.
And it's maybe good to add that it's, although there's software available, yes, that's right. Thank you, Renee. It's always best to write your own codes. They are much more efficient and much more specific.
That's almost always the best approach.
Okay, I don't see any more questions in the chat or in the Q&A. I think let me give a short moment just to see if there are any other remaining questions, any burning questions. If not, thank you everyone for attending, and you are most welcome to contact Towan and me by email if you have any questions. And yeah, as Renee has pointed out in the chat, the recordings are on YouTube, so you can watch them and watch them over and over if you like, if there are certain concepts that you don't understand. And please always feel welcome to come back to us with any questions. So thank you very much for attending. And Renee, I'll give you the honor to say the last words.
Thank you very much. Indeed, it is my honor to thank the two of you, Towan and Tjaart. Thank you very much. And also to our online participants, our audience, thank you for being here today. And for everybody that will be watching this on our YouTube, I see that the first lecture in this series has already amassed quite a number of views. So that just goes to show what a wonderful initiative this series is, and how many people are benefiting from this initiative and many other like this. So thank you very much again. Thank you for all the effort. Thanks for putting this together. And then next week we'll meet for the last session, last installment of this series. So thank you once again to everybody here, and we see you next week. Thank you. Take care. All the best. Bye-bye.
Thank you.